Hello and welcome back to another episode of Statistical Ninja Training. I am your host, Sensei Stats-A-Lot, and today we have a very special guest by the name of Earl Johnson. So Earl Johnson, please introduce yourself.
Well, thank you very much now. It's a pleasure to be here and have the opportunity to speak with you about something that I found very important, which is regression. And using regression for some data mining strategies here. So that's what we're going to talk about. And feel free to send me an email or a comment below if you have any questions here.
Thank you. And let me just say one more thing. It's a real pleasure to have Dr. Johnson. It's a real pleasure to have our esteemed colleague here to talk to us about some of the issues related to regression, because he is the world's foremost expert in what we're going to talk about today. So without further ado, let us get on with regression and data mining techniques. All right, so in regression so far, what we've talked a lot about is about hypothesis testing. And so we use regression as a means of testing hypotheses. And what that means is that we formulate a hypothesis that maps into a very specific parameter, such as the one and only interaction term or a single main effect that is controlled for another factor, something like that. And we have also talked about setting a personal decision criteria. For example, the standard decision criteria is a p-value less than 0.05. But we could also decide that we set our own decision criteria based on the slope, for example. You could say the slope is greater than 0.5 or the semi-partial correlation coefficient is 0.05. You can set your own decision criteria, and that's totally awesome. And then at that point, we just follow the 8 steps and make a conclusion based on our decision criteria. But sometimes we aren't ready for hypothesis testing.
I say it ain't sometimes. I say almost all the time. You see, there's this misunderstanding psychology that exploratory modes and stuff, they ain't appropriate ever. And so what we do is we approach our data like it's with hypothesis testing tools. See, and that's a problem when we in EDA mentality. Yeah, exactly. And that's what we're going to talk about quite a bit today, and how we can actually leverage the tools of EDA for doing some of the things that regression is actually good at. So we've got 3 reasons for using regression. One is confirmatory, which we already talked about, which is hypothesis testing and effect size estimation. But we could also use it for exploration, which is hypothesis generation, and we could use it for prediction. And these last 2 I consider data mining strategies. Now hold up a minute now. Now I don't think that's fair to be calling EDA a data mining strategy, because data mining ain't the same thing as EDA, and that's part of the misunderstanding.
Yeah. Because data mining kind of gets a bad rap. Basically, a lot of people perceive it as atheoretical, that you just plug it into an automated software and the software prints it out for you and does all the thinking for you. And that's kind of the standard approach to data mining, wouldn't you say?
Oh yeah, in EDA it's anything but that. You see, the most important point here, the most important take-home message for you and for me and for you is that your intention is important. You understand me? So if you're fishing because you're curious, you want to learn more about the data, well then you in EDA mode, you just fine as long as you're transparent about it. But or you want to deepen your understanding, see? But the problem is if you're fishing because you just want to find something that's publishable, well that ain't good here. That ain't good at all. And that's what data mining is. Well, not even data mining, because data mining has its strengths in certain situations where you're brand new to an area and you just got to put it in the algorithm and the algorithm find it for you. But the problem here is that ain't right. That ain't right. Well, I just lost my train of thought. What was I saying again? I don't know. Yeah, we talk more about that later. Yeah, we'll get into it later. Thank you.
All right, so data mining, prediction and exploration, but maybe not the best term for what I'm talking about. Basically, these are strategies. What I'm considering data mining are strategies that we use when we don't have a very strict specific hypothesis, but instead we're a little more open to some exploration. And so prediction versus exploration. Prediction means we don't really care about explaining anything. Now hold on here. I wouldn't say that's true. Sometimes prediction is the first step. You understand? Prediction is the first step you take before you can start developing theory. So it's not that you don't care about it. You know, you're just trying to predict the future, but you start developing some hypotheses about what those important variables are. Yeah, exactly. Yeah. But at the first stage, you really don't have theory to back anything up. You're just trying to predict whatever it is that you're predicting, and that's kind of a first stage. So examples of this might be stock market and student retention. You know, for example, if you're new in an area about student retention, you might really only care about predicting who's going to drop out of university, and that's why I put those kindas in there. Yeah, I think those kindas are important. Because sometimes when you're doing a model of student retention, or like the third one you got there, who's at risk of suicide, in those situations you might not know what variables are important. You just want to predict, and that'll give you a smaller set of predictors that you can then use for digging a little deeper. Know what I'm saying? Yeah, exactly. So it's kind of a first step. In which case maybe prediction and exploration aren't really that different, because they're both hypothesis generating procedures. But exploration, I see, as more of a little more theory driven than prediction. Yeah, I think that's fair. And so, or another example of kind of a prediction or a data mining strategy would be identifying genetics that are related to intelligence, or any sort of genetics that are related to any sort of disease. And, you know, I worked as a biostatistician. That's a lot of times what the bioinformatics people were doing. I didn't do much genetics, but a lot of people in my lab, that's exactly what they would do, is they would use some of these prediction models to reduce the subset from millions upon millions of genes to the small number of genes or SNPs or whatever they call them that are actually predictive of the disease. So that's kind of prediction, whereas exploration, we very much care about explaining. We very much care about understanding what's going on, but we don't know enough to offer a very specific, strict CDA hypothesis. So EDA, like I said, is driven very much by theory and by curiosity. And perhaps, which is I think what we're concluding, these two purposes are really closely related and may not be all that different from one another. All right, so let's talk a little bit specifically about predictions. So sometimes all you care about is predictive accuracy. For example, you might want to figure out who will become an active shooter. That's an important question to know. And at this point, we no longer really care about which variable gets credit for the prediction. We just care about predicting the outcome. But that introduces a whole new problem. So multicollinearity, not as much of an issue, but we do have a whole new problem, which actually is closely related to multicollinearity, which is cross-validation. So let's say we have a model and we fit it to some data that we've collected, and we have this kind of generic model. So we got this model. It could be a regression model or some other function. And so we might say active shooter. The probability of somebody becoming an active shooter is a function of depression, their antisocial score, socioeconomic status, fatherly support, motherly support, violent video game usage, their weight, their height, hours worked, and the number of violent Facebook posts or something like that. So obviously some of those variables are probably going to be predictive, whereas some of them aren't. I'm guessing weight and height won't be all that predictive, but we want to know from this large set of variables which ones are best predictive. And so suppose we fit the past data with 95% accuracy, however accuracy is defined. Now I know this isn't standard regression, but go ahead and stick with me for this example. So do you think we'll have 95% accuracy in the future? Oh, definitely not, definitely not. Exactly. And that's the problem with all models, not just regression. Regression is particularly susceptible to it, but all statistical models have this problem. So we fit the data, and let's say we get 95% accuracy or whatever, some metric that is impressive, it's highly likely, in fact, it's almost impossible for this not to happen, that if you then try to use that same model on a new data set, it's not going to cross-validate very well. And if that's the case, then what has happened is we have, quote-unquote, overfit our data, which means we have fit both the signal and the noise, or as Tukey put it, we've both fit the rough and the smooth parts of our data. So what does overfitting mean? Well, look at that. Well, I was going to talk about it anyway. So in a regression model, we have two parts. So a standard, simple regression is y is equal to b0 plus b1 times x plus e. Well, what we call the b0 plus b1, that is what we call the signal. And then e is what we call the noise. Or like I said, as Tukey called it, y is equal to smooth plus rough. And so what we're doing when we are using statistics is we hope to capture the signal that exists in the world, but leave behind the noise. So sometimes we accidentally fit the noise, and what this is called is overfitting. And this can happen just by chance. Sometimes just by random chance, patterns emerge, and that can be problematic. So the larger the number of variables we use, the higher the probability we will overfit the data. So, and let me just clarify what overfitting means. Well, let me tell you what overfitting does not mean. And I think this is a common misconception. So at time one, let's say you fit a model with a particular variable set, where fit means that we plug it into the statistical machinery and then it finds the optimal slopes that minimize the sum of squared errors. And then at time two, we fit a model with the exact same variable set. Now that word fit is important, meaning if at time two we are finding a new set of optimal slopes, that is not what overfitting is. That's just using the same variables and allowing the algorithm to fine-tune the parameters across different conditions. So if we fit a model twice, that's not measuring overfitting. Okay, so how do we measure overfitting, or what does it mean? So what that would mean is, at time one, it's exactly the same as before. We fit a model with a particular variable set, where again, fit means we find the optimal slopes. And then at time two, what we do is we don't fit the data. We use the exact same slopes and intercept that we used at time one on the new data set. So there's actually no fitting involved. We are just predicting the new scores based on the old regression weights. And how we assess the degree to which we overfit is you might compute an R squared in the second model. So we have a prediction for the second data set. We have a prediction for the second data set, and we then compare the prediction generated by the second data set to what was actually obtained. And the vast majority of the time, your R squared drops pretty substantially when you do that. So the idea is, if we're predicting the future, we don't have access to the dependent variable. So we can't fit future data, but we do have access to the independent variables. For example, your intelligence probably isn't going to change in the next 6 weeks, your socioeconomic status, your height, your weight, those sorts of things. So we're going to use what your values are today to predict what you're going to be 6 weeks from now. So how do we avoid overfitting? Well, there are actually 3 strategies we can use, and they're all different ways of thinking about a cross-validation sample. The first is that we can use a holdout sample. So the idea here is that we use 70% of the data to fit the model, and then we retain 30% of the data to actually test the fits of the model. And the fit of the second sample will almost always be poor, just as it is in any kind of cross-validation setting, but it's a fairly good approximation to how well the model is going to perform in the future. But a holdout sample will almost always, a holdout sample, the fit of a holdout sample will almost always be better than the next strategy, which is collecting 2 independent samples. And the reasons for that are a little technical, and if you have questions about why that is, we can talk about it in class. But that's the second strategy, is that we collect 2 independent samples. It's a much better strategy to use if you can afford it. And then step 3, or the third approach, is kind of these built-in holdout sample ideas. So this is kind of a, I don't know, an automated way of doing it, I guess. So a lot of statistical packages allow you to do leave one out cross-validation. And basically what that means is you use all the data points but one of them. You just randomly leave one out and then predict the value of that one data point. And you do that over and over and over and over again, and it will give you some metrics about how well it's predicting the one data point that it didn't use to fit the model. So all these strategies will tell us if we are overfitting, but they don't tell us how to avoid it. But they can help us identify which variables tend to overfit and which variables we might want to eliminate. Any additional things you want to add to that, Professor?
You done just fine there.
Thank you, I appreciate that.
But how do we avoid overfitting? Well, that's a tough one, really, because models are designed to find the best fit of the available data, and it's going to optimize that. And the problem is that when it's trying to optimize that, it's inevitably going to find some error there, and it's going to fit that too. So one way we can do is variable selection strategies. See, the idea is the more variables you have, the higher the standard errors. And the higher the standard errors, that means the model's more uncertain about what it's going to predict. And so that means it's going to be worse fit in the future. So one of the goals of regression is to identify the smallest number of predictors possible to predict. You understand what I'm saying? So you wanna make sure that and that's that little figure at the left there. That's a good figure. So mean error, or your accuracy in the model, goes down, or the future predictions rather, they go down as your model becomes more complex, which means as you have more variables. And so there's kind of this optimal point where you're going to have good cross-validation error and low bias. Exactly. And so how do we select the best predictors? Well, there's lots of strategies we could use. One tool in regression is stepwise. And I don't think there are very many statisticians, if any statisticians, who believe that stepwise regression models are good. They're just bad. So the idea is, so there's forward selection or backward selection. The basic idea, let's just talk about backward selection, is if you've got 10 different variables, you put all 10 variables into the model at one time, and then you eliminate the one with the smallest R squared or the largest p-value or something like that, and then refit the model. And then you keep doing that until you get to a point where you can't drop any more variables without significantly hurting the model. And the problem is that regression is super sensitive to variable combinations. So let's say, taken together, you've got a predictor, let's say socioeconomic status, that would be extremely important if it were combined with 2 or 3 other predictors. But when you look at the entire data set as a whole, it hardly adds anything. And so that one is rejected, but it would have been really, really good to use if it were only measured against different sorts of variables, if that makes sense. So that's stepwise regression. But like I said, it's super prone to overfitting. Again, stepwise doesn't respect the order of entry. And another limitation of it is that, well, I'm not sure that this is necessarily, well, yeah. Not sure it's a necessarily a limitation of stepwise itself, but it's more of a limitation of regression. In order to identify the strength of an interaction term, you have to explicitly model it in the regression. And so if you wanted to know whether there were strong interaction effects in the data, you would have to specifically put all the interaction effects you think might be there and then plug it into a stepwise regression, if that makes sense. And actually, I'm not even sure if regression
because like with an interaction effect, if you got two variables A and B, and you have an interaction term for A and B, and you're doing a stepwise regression, and it finds that it drops A but retains the interaction, that doesn't actually make sense to drop A when there is still an interaction with A in the model. So I'm not sure if stepwise regression natively understands that, and I don't know. Regardless, just pointing out that I know nothing about doing interactions in stepwise models, and I don't like stepwise models anyway, and in those situations I'd use a different strategy. So take my word for what it's worth. Professor, do you have anything to say?
No, I don't like stepwise either. So yeah,
thank you. So mid-lecture summary, if we're confirming a hypothesis, we only care about one parameter, then very specific, strictly CDA a priori hypotheses protect us from issues of multicollinearity.
Wait a minute. I'm not sure that's the case. So you're saying if you predict a hypothesis in advance, did it protect you from multicollinearity?
Yeah, I think. It seems to make intuitive sense to me.
Well, I don't know if that's true. I never thought about that. That's a good question, and I'm not sure it will. It requires some simulation to find out if that's the. Well, I don't even know if a simulation would do it. You know, that's a good theoretical question. I don't know. I'm not sure it's that set in stone.
Yeah, and I'm not sure either. You know, that's just kind of my gut feeling that it would protect you from issues of multicollinearity, but I'm actually not sure if that's the case. Let's think about that. If you have any insights, let's talk about it later, or comment, y'all. But one thing is sure is that replication across repeated conditions will address the issue of multicollinearity. So if you're concerned about multicollinearity, then you could do an experiment, and if you randomly assign people, then random assignment by definition is uncorrelated with everything, so that will totally get rid of the multicollinearity issue, and that will help you identify causal relationships, which is what you're interested in here.
Yeah, I think that's fair. Replication, that's probably, like you said, across repeated conditions, across different conditions. That's probably your best bet against multicollinearity, and really the best bet against multicollinearity is that, and more just the idea that it's what you find in one sample isn't the truth, and that's the problem, is we treat it as the truth when it ain't the truth, and so that just gives us some avenues to further explore and further discover. And so if you find a particular effect and you're concerned about multicollinearity, what it basically means is you gotta study that a little more. You know, in a different study, in different population, under different conditions, different designs, those sorts of things. Yeah, exactly. And it seems like there's this culture of rush in psychology that, you know, you find this and then you move on to the next thing, and you're just finding phenomena after phenomena, and without really spending time on digging into what it is that you actually have here. Yeah, exactly.
Also, again, back to the mid-lecture summary, we may only care about prediction. If so, overfitting is an issue, and we have to deal with that. And the best approach to identify when it happens is cross-validation, and the best strategy to combat overfitting is to identify as few predictors as possible. And the final mid-lecture summary is stepwise sucks.
Oh yeah, that if you take home nothing else, then that's a good one right there. Stepwise sucks.
Thank you. So now we're going to talk about random forests, and random forests are just amazing. I am extremely fortunate and lucky that I worked for 3 years as a biostatistician, because I probably never would have heard of random forests had I not been involved in biomedical research. And they are, it's a fantastic algorithm, fantastic modeling strategy that has so many uses in lots of different ways that a lot of psychologists don't know about. So this is cool that we get to talk about this here. So random forests are based on decision trees. So on the right is an example of a decision tree. So you would start with a question like, does it have more than 5 legs if you're trying to identify an animal? And so that would be predictor 1. And then if yes, then you would go on to predictor 3 in this case. Is it hiding under your bed? I don't know if I've actually read through all these. I don't even know what this means. Anyway, let's say the answer is no. This animal that I'm trying to identify does not have more than 5 legs and is not, or does have more than 5 legs and is not hiding under my bed. And so the next question is, does it make honey? Yes. Then it predicts that it's going to be a honeybee. If not, then it predicts it's going to be a mosquito. Okay, so that's basically what a decision tree is. It's kind of this nested idea of variables. You have one variable that you ask a question about. Is it this or this? And then you go to a new stage and you basically make a tree. So random forests are based on decision trees, except rather than using all the variables, so let's say you have 10 variables, that would be 10 hierarchies here. So in this one we have 1, 2, well, no, not 10 hierarchies. So this has 1, 2, 3, 4, 5, 6, 7 variables. I guess 10 wouldn't be too bad, but let's say you have 400 variables. That would be a massive tree. So random forest, it doesn't actually use all the variables. What it does is it randomly samples some of them for each decision tree. And then at the next step, using this subset of variables, it randomly samples 66% of the data set, or 2/3 of the data set. And then with that 2/3 of a data set, it builds a decision tree using the small number of variables that it already selected. And then what it does is after it fits that tree with the 66% of the data, then it uses the remaining 33%, which Random Forest calls the OOB, or out of bag sample. So it uses that one decision tree to then predict the scores for the 33% that have not been used to fit the data. And then subsequently it creates another decision tree. And this second decision tree is now going to randomly sample a new set of predictors. And again, it's going to randomly sample a new 66% of the sample, and again, cross-validate on the 33%. Now, one thing that's important to remember here is that 66%, that actually ain't a random sample of 66%. It's a bootstrap sample, so it's sampled with replacement. Yeah, that's important. So, and we haven't talked about sampling with versus without replacement. If you're interested, we can talk more about that in class. But basically, the idea is there's a possibility that somebody could get selected twice. Yeah, exactly. So basically, that's the idea. So Random Forest creates one decision tree based on one set of predictors and one subset of the sample. Then it creates another one based on another set of predictors and another subset of the sample. And then what it does is it does this many, many times, like 2,000 times or something like that. And that's why they call it random forests, is because you have a ton of decision trees. You have like 2,000 decision trees. And so here's just some R code for your enjoyment. And so this is the NSDUH dataset. Now this PowerPoint shows how you would read it in as a CSV, or it's part of the FIFER package, so you can just load it from the FIFER package by going data, open parentheses, NSDUH. And then what I'm doing here in the second step is I'm omitting missing data. All right, so we haven't talked about missing data yet, and this isn't the best strategy to handle the missing data, but without a lot more background, I wouldn't be able to kind of help you figure out. Anyway, we'll do that now, and then I think next week we're going to start missing data. So, and then the other thing that I'm doing is I'm only sampling 300 observations, because the thing about random forests is it is extremely computationally intensive. And so if you, I think the NSDUH data set is 45,000 observations, and if you're going to do a random forest on the entire thing, it's probably going to take hours. So here's the code. You require a random forest to load the random forest package. Of course, you're going to have to install that first, and then the date, or the what's the word I'm looking for? Syntax, that's the word. The syntax is pretty easy. It's WHODOS and Periment, And I spelled impairment wrong, that's my fault, but that's basically how much impairment you have as a function of your mental illness or whatever. Tilde dot, which is basically shorthand for saying use all the variables to predict impairment, and then data equals M. Of course, there's options that you can change, but I tend to stick with the defaults. And then what you can do is plot RFFit $R squared, and that gives you a plot right here. So on the x-axis or y-axis is the R squared of the model, and on the x-axis is it tells you the R squared of the forest containing trees through 100. So basically, if you have one decision tree and then predict your entire data set, that's what that point says. And now it says, all right, let's see what happens when we aggregate, because what happens at the end of random forest is it then uses all the trees that you've developed to generate a prediction for every single individual. So it aggregates those trees. And so basically this is just showing how the fit of the model improves as you increase the number of trees. And it looks like at about 100 trees, the fit doesn't seem to improve that much. But we're looking at, you know, almost 0.75 R squared. So we're explaining 75% of the variance with this model. But again, at this point, this is using all the other variables in the model. So there's some concern about overfitting. But one other thing that's important to note, which is this note right here, is that those R squared values are based on the out of bag set. So it's telling you 75% of the variance is explained in the data that was not used to fit the model. So that's actually pretty impressive. So that's a cross-validation R squared we're looking at. So that gets us to the idea of variable importance. So after random forest grows 200 trees or 500 trees or 1,000 trees or whatever it grows, it can then assess variable importance. And it does so, and I'm going to oversimplify things. There's actually lots of different measures of variable importance. But essentially, one way of assessing variable importance is to drop the variables from each tree and then run people through that same tree without that particular variable and see how much worse the fit gets when you omit that variable. And that's the essential idea behind it. And so if the fit drastically changes when you eliminate MI, for example, which I think that's the probability of mental illness, then what that tells you is, and don't worry about the increase in node purity. I think what that means is when you put it back in, how much does it increase your ability to predict? And anyway, I'm oversimplifying things, but you get the idea. So that tells you that as you drop MI compared to when it was in, it makes a huge difference. And so this tells us that our most important predictors are mental illness, distress, whether you've had depression in the past year, whether you've had a major depressive episode the last year, and then age, and then it gradually tails off after that. So again, these are predicting, impairment. So mental illness, distress, and depression the past year are by far the best predictors. So choosing the number of variables. And this is where it gets a little iffy. So you might look at this plot and say, all right, so how many do I include? Well, not really an easy answer to that question. There are algorithms out there that use some sensible criteria for determining when to stop. I'm not going to go into the details here. I'd be happy to give you the reference to the paper that I use for doing this. The problem with this algorithm, it's actually not a problem if you got time, is that they take a long time to run. So the algorithm that I use that is built into the FIFER package, basically what it does is it creates dozens of forests. Now remember, random forests are hundreds or thousands of decision trees. And so what this algorithm does is it creates multiple forests. And the idea is that if you have multiple forests and then estimate the variable importance across these multiple forests, you have some estimate of the variability of variable importance measures, and then you can start using that to make decision criteria and that sort of thing. And since y'all are FIFER package users, I've done all this for you. Can I get a thank you?
Well, thank you very much, sir.
And thank you, Professor. All right, so here's some code that you could use in the FIFER package. Basically, there are 3 stages to this algorithm: the threshold stage, the interpretation stage, and the prediction stage. We can talk more about what those mean in class, but basically each stage is a winnowing down even more. So the threshold says, all right, what predictors can I just get rid of because they make absolutely no difference? Interpretation says, all right, let's winnow this down a little more to find those predictors that are that we might want to interpret for theoretical reasons. And then the last one says, all right, if I'm only interested in prediction, I want the minimal set possible. So let's winnow it down a 3rd time. And then plotting, that just shows the plot. That was before I was terribly proficient at plotting, and I haven't gotten around to modifying the plot yet, so of course the text is cut off, but you get the idea. And then when you just ask R to show you what is in the 3rd model, it will show you the objects that are contained within that, and it will give you a summary saying the remaining variables are these. And what it says is this last stage took 14 seconds to run, which actually isn't bad at all. Some of the earlier stages take a whole lot longer. So that's the basic idea of how you select variables in FIFER. But again, be prepared to binge watch Netflix or something because it might take a while. All right, so advantages of random forests. It has built-in cross-validation components. So RF almost always outperforms regression cross-validation on a brand new sample because it's already got that built-in cross-validation component, which is fantastic and awesome. Another advantage of random forest, which is absolutely phenomenal. It is amazing. It is brilliant. It has saved my life so many times, made so many analyses so much easier, and that is that random forest natively detects interactions. So with a regression, you have to explicitly specify whatever interactions you think are present in the model. And if you don't explicitly specify it and it is there, then you're going to have a messed up model because it's not accounting for that interaction. And so it requires a lot of thought on the user, which isn't a bad thing. You know, thinking about your statistics is a good thing. But random forest does all that for you. It natively detects interaction. And so if a variable has high importance, whether it's important because of a main effect or an interaction effect, it doesn't matter. RF is going to say this variable is important. And a final advantage of random forest is that it is non-parametric. So you don't have to make any assumptions about the data at all. And that is so awesome. So random forest, it's pretty legit. Disadvantages of random forest, and these are disadvantages that make it limited. So one is that it's what we call a black box algorithm, meaning that so like if you were to run a regression on a data set, you could report the regression equation that you used, and somebody could read your paper and make predictions on an independent set of data using your data, or using your prediction that you put online. Well, the problem with random forest is that the quote-unquote equation is 2,000 trees. And so basically it's 2,000 if-then statements that have lots and lots of nesting. So you're talking thousands upon thousands of lines of code for the equations. And that's kind of frustrating. It's not like you can go online and, you know, put your entire random forest algorithm in the appendix. That's going to take hundreds of pages. So that's a limitation of random forests, which is not a limitation of regression. Another disadvantage of random forest is that it's hard to visualize-ish. So random forest will tell you how well it predicts and which variables are important, but natively it doesn't tell you exactly how they're important. So at the end of the day, you're like, all right, I know which variables are important. Now what? How do these predictions differ from a regression, or what are they predicting? I don't even know if this is actually making sense. And so that's a limitation of random forests, but it's actually not because of some work that, not that I have done. I mean, I basically stole the idea from other people. Other people say, well, let's go ahead and just show the predictions. And we can then visualize exactly what regression is doing to fit the data. Or I'm sorry, what random forest is doing to fit the data. And fortunately, within the FIFER package, that's super easy to do. So that's my tiny drop in the bucket, my little contribution, that I've got an easy way that will make it super convenient for you to visualize what a random forest is doing. So, overcoming these limitations. How do we overcome the limitations of random forest? So, random forest is a black box. Well, regression is not. Random forest doesn't tell you how variables are related, but we can output the predictions and visualize them. So here is my strategy that I use all the time when I'm doing kind of exploratory data analysis with regression. What I do is I use random forest to identify a small set of predictors that are worth looking into. And from that small set of predictors, I build a new random forest model and then save the predictions based on that small number of variables. And then I plot them. And then I use those same predictors that random forest identified and plot the regression fits. And then what I do is I visually compare them and see how convergent they are. So if random forest and regression give similar predictions, then shoot, I'm going to choose a regression model. If not, then I settle with the black box.
Well, actually, you don't have to settle with a black box. One thing you could do is, you could look at the fit of the random forest and say, well, that function looks like it might be a polynomial, so I can use polynomial regression. Or maybe you have to do some generalized linear model or something like that. Yeah, exactly. So you're not resigned to random forest. It's very good for winnowing down the list of variables. And if you are in a situation where you need a simple prediction equation, then it can guide you in identifying what model might be most appropriate. So here is some ways that you can choose variables. So I think we've seen all that first part, the threshold, the interpretation, and the prediction step, and then saving the model. And then what we can do is we can compare the prediction. So I'm creating a model. And so when you do these RF-pred, these FIFER functions here, the function actually stores the random forest model within that object, the third.mod. And so to extract the random forest model, you just go third.mod $model and store it in a variable called model1, or you can name it whatever you want. And then we can create a second model, which is just a linear model. And all I did here was, this is short code, so model1 $terms. That just gives you basically the variables used in the equation, and I turn them into a formula. And then, so this right here will give me a regression version of the same variables. And then this function right here, compare.fits. Oh, look at that. I'm already going through there. All right. It visually compares the fits, and so it will show random forest in one color and regression in another. And by the way, y'all owe me big time for this one, because this is going to be super, super, super helpful, especially as we get to generalized linear models. But it's really helpful anytime you're trying to decide between two different ways to model the data. It's very, very convenient to be able to show the predictions on one graph. So here's an example of that. So some questions you might want to ask yourself. So the dashed line here is the regression version, and then the solid line is the random forest version. So some questions we can ask: how did the two models compare in terms of fit? Well, it sure looks like the random forest data is, or the random forest model is following the data a lot more than the regression model, because again, the regression model has to be a straight line. So another question: how does regression say, or what does regression say about the relationship between mental illness and impairment? So regression says
that it's linear, that the more you increase in mental illness, the more you will be impaired, and it is a straight line relationship. But random forest, on the other hand, says you basically reach a threshold. You know, as you increase in mental illness, it looks like about 0.15. So if you have a 15% probability of mental illness, you're going to be vastly different than somebody who has a 10% or a 5% probability of mental illness. And you're going to increase rapidly from 0 to 0.15-ish or whatever it is. But then after that, it kind of levels off. So if you've got a 15% probability of mental illness, and you're being compared to somebody who has an 80% probability of mental illness, well, the difference in impairment isn't that much. And that seems to be what the data are saying too. And so random forest is really capturing some interesting stuff here. How many people are depressed and have little stress? I'm not sure what I meant by that question. So certainly, it's looking like random forest is doing a whole lot better than regression here. And it also tells you the relationship between these variables. So we already talked about mental illness, depression in the past year. So if we compare the fits, it actually doesn't look like having depression in the last year versus not changes all that much, but it does seem, well, problem is there's not many data points over here. But it does seem to be that the predictions are slightly higher, but not much. So maybe depression in the past year isn't the most important predictor. And what about distress? So for low levels of distress up here, if we just so this maxes out just over 10, whereas this maxes out at almost 20. So yeah, it looks like distress is making a big difference. So gradually, as you increase distress from low to high, your impairment increases. And are there interactions? And again, what I'm looking for is, does the shape of the line change much? Well, I guess in the depression in the past year, no column, there's kind of this sharp bend. Whereas if there is depression, then there's kind of a little more of a gradual bend. So, I mean, this is the sort of plot that requires a little higher cognitive load. And so maybe we could talk more about this later, but those are just my initial impressions of what the data are actually trying to tell us. So let's remember this strategy because we're going to use it a lot for the rest of the semester. So step 1 is fit a model, step 2 is fit another model, and step 3 is we visually compare the fits. All right, so mid-lecture summary again. So with lots of variables, it's easy to overfit the data. Regression solution, which is stepwise, really sucks. Random forest is amazing at identifying important variables. But random forest doesn't give a prediction equation and doesn't tell you exactly how each variable is related to the DV. So we can combine the advantages of random forest, which is cross-validation and variable selection, with the advantages of regression, which is visualization and easy mathematical solutions. And the end result is we have a model that we can use for good prediction. And in reality, we're really not combining the advantages of random forest with regression, meaning we're not borrowing regression's easy visualization. We're just outputting the predictions from random forest. And we're not using regression's easy mathematical solutions. We're just comparing random forest to regression and using regression if the differences aren't that major. So uses for random forest. I'll just talk about this quickly. So we can use random forest to find an optimal set of predictors, which is what I just showed you how to do. We can also use random forest in a simulation. Most of you won't be here because you're not doing Monte Carlo simulations like I am, but I use them all the time. Like if there are 15 parameters of a Monte Carlo that you're not sure which are important to vary, you could randomly vary them and then use random forest to identify which of those actually make a difference in bias. If you don't know what I said, totally cool. We're still friends. Okay, number 3, we can use it as a non-parametric regression, which we actually used it here because the relationship between mental illness and impairment wasn't linear, and so we can use random forests as a non-parametric prediction tool, or we could use generalized linear models, but we can use random forest for this reason. We can use it to identify interaction effects. And finally, which is kind of what I did and very closely related to the first use as well as the fourth use, we can figure out which variables are worth plotting. So if we have 10 different variables and we want to see the relationship between, obviously we don't want to look in 10-dimensional space, that's just too much cognitive load. And so what we can do is we can run it through the random forest algorithm, and it will tell us which variables we should actually be interested in plotting. So exploratory analysis. So when do you use it?
Hey, do you mind if I take this one?
Oh, absolutely, yeah.
So whenever we're new in this area of research, that's a good time to be using exploratory data analysis. So for example, maybe you never explored the dependent variable before. So maybe cyberbullying back in the day, nobody looked at it yet. Well, now people looked at it, but back in the day, you might not have ever used cyberbullying, might not know anything about it. Or maybe you're bringing new predictors to the table. So you got a variable lots of people have been studying, but you want to introduce a new predictor. Well, we don't know anything about that predictor. So that's when you use exploratory data analysis. Or we might need to use it when we bring new combinations of predictors to the table. I see this all the time, where you got many single variables studied in isolation, like somebody looked at depressed and schizophrenia, or somebody else looked at depression and social isolation, but nobody combined the two. And so we don't know what we can predict here. And so in that situation, exploratory, good. So as you know, combining variables complicates things when there's multicollinearity. And so, so another situation where you might use it is when we're not quite ready for strict CDA. So remember, in strict CDA, we got one shot at it. We can't compute more than one p-values, whereas we doing multiple comparisons. So in that situation, we can instead do rough EDA, as John Tukey called it. So rough EDA is basically using EDA tools with CDA purposes. So your purpose is to test your hypothesis. Well, we can use EDA tools for CDA purposes. Also, maybe we have done strict CDA, but we want to see if there's something else there. So maybe we also collected additional variables that we might use for some more hypothesis generation. So in those situations, you might ask yourself whether there's relationships we can explore further. And just a reminder, we're going to talk more about this in the next couple of slides. So many research studies use confirmatory tools and confirmatory rhetoric, or the words they use, when they actually in exploratory mode. So they compute p-values, do t-tests, and novas, and regression, those sorts of things, when they don't quite know what their hypothesis is, or maybe they got a vague idea of it, but they ain't ready for strict CDA. And so in that situation, it don't make sense to compute a p-value because you ain't ready yet. And so that's what the confirmatory tools is for. I'm sorry, that you use exploratory tools, you know, effect size measures and graphics and those sorts of things. Now something to ask yourself, does your research sound like any of the above? So are you in a new area of research? Are you not quite ready for strict CDA? Or maybe you have done strict CDA, but you want to do a little more exploration. Well, maybe it's best you consider your research exploratory research. So remember, if you have a very precise hypothesis, it's CDA. Otherwise, it's EDA. And so that gets us to the 3 commandments of EDA. No, I'm sorry. That's the 4 commandments. Looks like there was an error there. So the first one, thou shalt not hawk. So hawk stands for hypothesizing after results are known. So in other words, EDA, you can't use EDA tools to find something, then test what you found on the same data set. That don't make sense. That's like looking for a rare coin, then you find it, then you test whether you found it. Well, of course you found it. Because you found it, of course. You don't need to test it. You found it. And so what people often do is they start looking for things, and then they find something, and then they report a p-value, and then they write their paper as if that's what they predicted in the first place. That ain't right there. That ain't right. That's just not cool. So thou shalt not hawk. Number 2, thou shalt EDA with the I forgot the not there. Oh, that's not good. That should be a not. Thou shalt not EDA with the intent of churning. So sometimes people, you know, they do an experiment, they contact the IRB, they go through all that trouble, and then they do a study, and studies don't work. They don't get P less than 0.05, which, you know, maybe you should have been doing Bayesian or something, but that's okay. That's beside the point. But they want to salvage a project, and so they start saying, well, I better do something, or else this was a waste of time, a waste of effort. And so they start fishing. Well, that's a little problematic. Okay, if your intent is just to salvage a product, that ain't right. And likewise, you shouldn't be doing EDA with the intent of publishing something, because that's just going to lead to bad stuff. So if your intention is just to get a publication or just to advance your career, you should not be doing EDA at all. Okay? But if your intention is curiosity, if you just want to learn from your data, well, that's exactly what EDA is for. Provided that you're explicit about it, and that's commandment number 4. We'll get there in a minute. So commandment number 3, thou shalt cross-validate. So you find something via EDA, then it is your duty, your obligation, that you find it in EDA. You don't know whether you found it because you were looking for it, or whether you found it because it's actually there. So it is your responsibility to then cross-validate on a new sample. Okay, and step number 4, thou shalt be transparent about results. So when you write in your report, you need to be very explicit. Okay, which of these results were discovered through EDA? And which of those were discovered through CDA? And likewise, if you tried to do, that should say failed CDA attempts. If you tried to find something with CDA, you had a hypothesis, you did strictly confirmatory, and you failed, well, what do you do now? Well, you got to report that. You got to make sure you got to make sure the scientific community know that. And so you got to be very explicit. You got to be transparent about everything that you did and everything that failed and everything that worked. Now, sometimes you can summarize a little bit or say, hey, if you're interested in more information, because, you know, you don't want, there may be 10,000 steps. You don't want to talk about every step, because that's going to be a big paper. So you say, look, here on my website, here's all the steps that I did, but in short, this is what I did, and you're just trying to be open about it. And so those are the 4 commandments of EDA. Thou shalt not hawk, thou shalt not EDA with the intent of churning out a publication, thou shalt cross-validate, and thou shalt be transparent about results. Okay, so now we got the tool set for EDA and the prediction. And so the tool set is the same for both, and that's probably because they both really the same thing. If you're doing EDA, you're doing prediction, you're doing the same thing. Yeah, exactly. So so the tool set is basically the same for both, but really there's actually more tools at our disposal for EDA. If you're interested, you can certainly look at John Tukey's textbook as well as some of the others. We use data mining procedures to reduce a sometimes extensive list of predictors into the best predictors, and then we can then use those predictions to predict future scores, find interesting hypotheses to further explore, or we can use them for both. So now, as your final practice, I want you to use the NSDUH dataset, and from that identify the best predictors of distress. And just for the safety of your computer so it doesn't explode, I would probably limit it to 200 observations. Then I want you to plot variable importance of these predictors, then fit a regression model using the same predictors, and then compare the predictions from both using the compare.fits function. So ladies and gentlemen, thank you for coming. It's been a pleasure to have you here, and we will see you next time.